I've called my talk tonight Fading Stars, Understanding, Measuring and Reducing Outdoor Light Pollution. And I've basically starting right at the very beginning. I'm assumed you know nothing. So apologies if you know everything. And you'll just have to excuse me for that little bit. But yes, that's what I'm doing. And I'm going to, oops, I'll just get my screen working again. There we go. So I'm going to start by telling you a little bit about me. Then I'll talk about what is visible light, which is sort of a rhetorical question, but I'll go into a little bit of detail about it. Then I'll talk about how electricity makes light. Then we'll go into light pollution. What is light pollution? How does it affect us and the environment? How can we minimize it? And how can we measure light pollution? Feel free to ask any questions you have along the way, and we'll see how we go. So let's begin. So this is me. I have a bachelor's degree in electrical engineering from a very long time ago now. And then I did a certificate in illumination, a master's in engineering, and as was mentioned, I'm currently doing my PhD studies. The reason that I'm doing that is because before 2010, I was a consulting electrical engineer, so I never set off in life to be a lecturer. It just wasn't on my horizon at all. And then in 2010, Massey actually asked if I would like to work for them. And I said, yeah, why not? But I only had a bachelor's degree at that point. So it was a bit unusual for me to work there and teach. And so I did my master's at that point because I had young children and I didn't want to sort of disrupt the family by doing a PhD. Now sort of life has caught up with me and I really have to do my PhD now because I am a lecturer at Massey, and it's very unusual for a lecturer to not have a PhD. So I'm catching up at the moment. So that's a little bit about me. In those images, you can see on the bottom left there, this is what I do for a day job. I speak. But these days, you'll more often find me online. Since COVID, I've done an awful lot of online teaching. And my main program that I teach is all about lighting. And all 4 courses for that have now turned into online teaching. So I do a lot of online teaching as well. As well as that, I look after the lighting lab at Massey University. So you can see top right, that's just me looking at a spectrometer, which I brought to show you later so we can try a few things out. And bottom right, that's a big piece of equipment behind me, which I didn't bring because that weighs about a ton. But that's also something that I play with in the lab. So here we go, starting at the very beginning. What is visible light? So there you can see I've drawn some waves on the screen. That's the electromagnetic spectrum. So you can see we've got lots of little waves on the left, so a high frequency, and that's where we have gamma rays, X-rays, and so on. And then at the other end of the spectrum, for the long waves, we have radio waves and things like that. In the middle, we have this little bit, which is still part of the spectrum, but it's the bit that we can see. So that's visible light. So gamma rays, X-rays, we know they exist, but we're not sort of seeing the stuff all the time, microwaves and so on. Radio waves, we can't see them, but we can see visible light. And so that's the definition, well, in Susan speak, visible light is electromagnetic radiation that is visible to the human eye, which of course we can see here as a rainbow. And if we look at that rainbow, you can see that it has all the colors of the rainbow, of course. And on the left, we have violet, which has a wavelength of 380 nanometers. So these are wavelengths that are moving very, very quickly, and they're really, really small. So of course, that's why we're measuring in nanometers rather than just meters. So that's violet. And when we're talking about light, incidentally, we don't talk about frequency. I don't know why. We always speak in terms of wavelength. So if you're a frequency person, we're talking wavelength today. So that's 380 nanometers at one end of the spectrum. And then at the other end of the spectrum, we have red, which is 780 nanometers. So between the 380 and the 780 nanometers, that's all the colors of the rainbow right there. And then, of course, beyond that, beyond red, we have infrared, which of course we can't see. And beyond violet, we have ultraviolet, which of course we can't see as well. So it's just that little snippet that we have in the middle, which is visible light. So how does electricity make light? There are different ways that electricity can make light. So the first example we've got here is the sort of the Edison kind of lighting, which is just heating a wire. And the wire is known as a filament. And when you heat that up really high temperatures, it will produce light. If you heat it really high, it will become more bluer. So it starts off, when you heat it, it sort of glows a reddy color, and then it changes, and eventually it will become this sort of bluey color if you really heated it up, which of course you can't because the wire would evaporate and break. So that's why these kind of lights are this sort of yellowy color. That light, of course, is not just white, it's all the colors of the rainbow which join together, and our brains go, oh, that's white. And so you can see here on the screen, this is all the colors of the rainbow, and this is what we get from an incandescent light source. So you can see we have a little bit of violet right up to a lot of red, and it actually keeps going and it becomes infrared, which is why incandescent light bulbs are very hot. And they're really inefficient because they're mainly producing heat. So they're really great at heating takeaways and keeping takeaways nice and warm at the takeaway shop, but they're not so good as a light source. They use a lot of electricity. So this here gives us an idea of the different colors that we get from this kind of light source. If we change to a different type of light source, this is a low pressure sodium light. So this is the kind of really old fashioned street lighting that you'd get, which had a really orangey color that you can see there on the right. That doesn't heat up a wire anymore. That is a tube and it has gas inside it. And the gas gets really excited and then that produces light. So you can see there now, instead of having the continuous spectrum we had before, we've got this one little peak here in the middle. And the reason we have that peak is because the gas inside, predominantly we had sodium in there producing the color. It's called a low pressure sodium light because that's what's inside. And that is the color that is produced when we excite that sodium. It's that yellowy color. And this is loved by astronomers, as you probably know, because this can be much more easily filtered out than another kind of light, which is full spectrum. So that's one kind of gas lighting. And then we also have another type of gas lighting. So this is high pressure sodium, which is still a tube with the sodium in it, but it's at high pressure. And that means that it becomes sort of a more slightly whiter color. If you compare, if you look at these two images on the right there. So that's the low pressure, that's the high pressure. You can see the difference, it's a bit whiter. And you can see that we have a broader spectrum here as well. So we've got a tiny little bit at this end of the spectrum, and then lots of yellow and orange and so on. So this kind of thing is what you would have found in Auckland for street lighting until LEDs took over, basically. And then, of course, we have LEDs. So we had incandescent, which was heating a wire. Then we had our sodium sources, which excited a gas. And now we're using electronics to make light. But the LED chips themselves, they can't produce white light. And so what they use typically is they use a blue LED chip and then they cover it with a special coating called a phosphor, and that converts the blue chip to all the other colors of the spectrum because we need all of these colors to make white light. That's what we're interested in. So this part of the spectrum, that's that blue LED chip. And then on the right, that's everything from that coating, that's from the phosphor. So that rather than just seeing blue, we see a white light. So this is the kind of thing that you would find in street lighting these days. This peak can change in size. So if you've got a really high blue peak, you get the really bluey white kind of light. If you get a lower blue peak, then you get more of the yellowy kind of light. So that's the blue peak is a bit of a problem when it comes to many people, and I'll explain why that is as we keep going. But I'm actually going to take a little step here to look at what is light pollution. So I've got this delightful picture that I drew with my amazing PowerPoint skills. And you can see we've got a house here. We've got a little bush here. Maybe there's a little animal living in it or near it. And then we've got this road over here. And and we've got our street light here. And so where you can see this light coming down here, this is the useful light. It's shining onto the road, and that's where we want the light to be, on the road. But we've also got all this other light going on, which is problematic. So there we go. There's our useful light on the road, and there's our spill light spilling all over the place. And we use different terms for that spill light. So first of all, we have obtrusive light, which is classified as light trespass. This is when light trespasses into your bedroom, for example, or into this little bush with this little animal. So that's trespass. Some people don't like the word trespass because they say that light isn't like a physical presence, like trespass to us means someone sneaking onto your property, which the light is doing, but it's not like a person or something. And so they don't necessarily like that term. And then we can also have direct glare, which is when some light is shining into your eyes. And so it's being a real problem in that regard. And then, of course, we have sky glow, which is of particular interest to you guys. So we can get sky glow in two different ways. First of all, we can get direct upward light. As you can see, our light isn't pointed straight downwards. And so we're getting some light shining up into the sky and affecting these up there. But we also get reflected light, because anytime light hits a surface, if that surface isn't flat, then it's going to reflect. And so we get reflected light as well. So that can be a problem. So even if our street lights are pointing straight down, if they're hitting something that's a light colored surface, that's going to bounce light up into the sky, which can be a problem. So how does light pollution affect us? Well, it affects us in many, many ways. And these are just some headlines that I grabbed from some newspapers. So you can see there, NZTA's introduction of blue LED lights raises a number of concerns. On the top right, LED street lighting harmful for urban wildlife. I'll talk a bit about that. Middle there, Northland LED street light retrofitting moratorium call. We've got a guy on the right there, effective LED street lights on autistic son. There's Damien McNamara on that Sky campaign. Down the bottom, the mad world of energy efficient street lights, and then we've got Western People's Day to buy LED street lamps. So there are a lot of concerns about light pollution, and it's really becoming a real hot topic. So there are different ways that light pollution can affect us. First of all, of course, light pollution can inhibit our view of the night sky. And this picture here on the left was taken by Reno, who came and spoke a month or two ago. My colleague Reno he took this photo, and then he did some processing using Photoshop on the right to, it's a bit hard to see on the screen actually, but I hope you can see the sort of the hidden stars that you can't see because of the light pollution. So of course that's problematic. And when we think about LEDs, that's particularly problematic, because remember that blue peak that I was talking about, blue light scatters more. And so that's why we have blue sky. And so that means that if we have blue in the surroundings, then it's going to bounce around a lot more, scatter more, which can be a problem. Another thing that can affect us is that the way that we operate is that, or the world operates, is that in the morning, we have a dim, yellowy colored light when the sun rises. Then in the middle of the day, we have a bright blue light overhead. And in the evening, we go back to a dim yellow again at sunset. So that's what naturally happens. The light changes during the day. But when we introduce electric light, it brings intensity and colors at times when they don't occur naturally. So for example, if you are looking at blue light in the dead of night, that's not what you're meant to be looking at, that kind of, well, ideally you'd be asleep. But certainly you wouldn't be having midday sun overhead, would you, in the middle of the night? So too much of the wrong kind of light can affect our sleep patterns. So there've been lots of studies done that show that this kind of scenario with the blue light can affect your circadian rhythms, your wake-sleep cycles, and that has just so many effects. Every day I see new studies of the things that are said to be caused by sort of light pollution or this kind of too much blue light. Examples being, last week I saw something on the onset of Alzheimer's, a lot of depression sort of things, cancer. And this is, I just looked up a few sort of titles to give you an idea. So the first one there, illuminating a risk for breast cancer, a preliminary ecological study on the association between street light and breast cancer. So that's one thing. Association between outdoor light at night exposure and colorectal cancer in Spain, and then outdoor light at night and the prevalence of depressive symptoms and suicidal behaviors. So there's all sorts of studies, and just be a little bit aware that these are scientists trying to find new things to write about. So, you know, you've got to read the fine print on all of these things and see what they're actually saying. And in many cases, they might just be saying there is evidence that this could happen. So don't go home and sort of be worried about everything. I don't want that to happen. But this kind of thing, what we see. So yes, so it's not just humans who are affected as well. Here are some titles that again I just found. So we've got reducing the blue spectrum of artificial light at night minimises insect attraction in the tropical lowland forest. So you can see the blue, people are talking about the blue a lot. Pollination and fruit infestation under artificial light at night. Light colour matters, and I'll talk about that a little bit later, about what's the best colour for us to use. And white and amber light at night disrupts sleep physiology. Oh gosh, physiology and birds, and movement responses of common of the bats to the illuminated urban landscape. So there are lots of different species, and they're actually all related slightly differently. So you can see there that blue was a problem for the insects, whereas amber was a bit of a problem for birds. So it's sort of a balancing act as well. So how can we minimize light pollution? Well, despite the fact that I'm a lighting engineer and I teach lighting all day long, everyone agrees that the best thing to do is to avoid light if we can, because, you know, we know that darkness is good for us. But we also realize that light is also helpful to us in various ways. And so number one is avoid light, but if you can't avoid light, then you need to consider a few things. So the first thing is you need to consider the intensity. Do you need to have all this lighting everywhere? As one thing. So maybe, for example, say you're going to a car park at night because you want to do your food shopping. Does the whole car park need to be lit, or just a little bit near the doorway? You know, because that's where everyone will park. No one's going to park on the other side of the car park at night time. So not only the intensity, but where the lights are placed. The timing as well. Do we need the lights on all night when people are probably asleep? And the color is really important as well, which I'll talk about a little bit more. But basically, as I said, the blue light scatters more. And so generally these days, we're heading towards lower and lower color temperatures. We're getting more and more orange again. And we're seeing that a little bit in certain pockets of New Zealand already. I know Dunedin has yellowy lights compared to the front, for example. And then we also need to think about the light fitting itself, because every light fitting has different optics and it has different height, could be aimed in a different way. Basically, we don't want to install a floodlight, which I'm sure you see all around the place, where it's mounted like this and it's just shining light straight out. It doesn't need to. It can go down and just light where it needs to be lit.
Poor installation going against New Zealand standards is also a big problem.
Yeah. Yeah, absolutely. And the problem is also who follows up from, you know, when something gets installed, who's going to follow up and chase that up? That's problematic as well. So how can we measure light pollution? This is something that I'm really interested in. It's the subject of my PhD. And so last year I published a paper that looked at all the different technologies that were available, looked at how they were used, what they were measuring, you know, how, for example, did ecological studies always use this kind of data, or did other studies use this kind of data? So first of all, we have spaceborne sensors. These are very commonly used. You get satellite data, and you can also get astronauts' photos from the International Space Station as well. And so basically these photos come, and then you can sort of code them, you know, look at all the pixels and work out which one's bright and so on, and work out what's going on there. There are a few pros and cons about them, which I'll talk you through. So there are two main satellites that get used a lot. They've got enormously big names, which get abbreviated. The great thing about that data is that it's free. Anyone can look it up online and use it. But a problem is that the DMSP one is quite old now. And as you see down here, this bullet point, it doesn't have onboard calibration. So you're getting all these images, but you don't know, like if you're trying to compare between the year 2000 and 2010, has brightness changed? We don't know, because we don't know if they had the same baseline, because it might have changed over time. Maybe something got dirty or that kind of thing. So that's tricky. They can only collect data on cloudless days, of course, because otherwise the clouds are going to block the view of the cities. They have low resolution, which means that one little pixel might be, oh gosh, I've forgotten. Might be a kilometer. I've forgotten. You know, you can't sort of go, oh, there's a light, there's a light, there's a light. So we can't pinpoint what's happening. There are saturation issues, which means that if you're recording near a city, it's just so bright that it just doesn't cope and it won't tell you any information at all. Critically, they're blue blind, which means that they can't detect that blue peak. I'll try and illustrate that over here on the right. The dashed lines, that's that LED spectrum that we saw before. You see it's got the blue peak on the left and then the rest of the colors on the right. And then here, this is what the satellite can see. And there, I've got the two different satellites there. The old one, DMSP, is at the top, and then the VIRS one is at the bottom. But notice that they cut off right here, and so they can't see that blue. So when they're doing these studies looking at light pollution, it's very hard to know what's going on when you can't pick up that critical part of the spectrum. They also, they don't capture a ground-based view, so they see what's going up, but we also need to see what's happening around us as well. The first satellite that I mentioned, the DMSP, is now considered outdated, and so if any people use that for research, really they shouldn't be. But thankfully, other satellites are available, and they might have better spectral data, but unfortunately, not all of them are free, and some can be quite expensive. So that's satellites. When we look at the International Space Station, you can go online because it's also free, and you can find pictures like this. See, that's a picture that I just grabbed from online, and then I worked out what was happening there. I could see the Harbour Bridge at the top there. I could see the CBD, Ports of Auckland there, Auckland Domain in the middle there, and Newmarket and so on. When you're using that kind of data, it has limited coverage. They're not taking photos all the time to do this kind of thing. Also, they have a few calibration issues because there are windows and so on that you're looking out of, and so that can attenuate the picture. And of course, again, it doesn't capture a ground-based viewpoint as well. We can also get airborne sensors, so we're not in space anymore. Now we're just lower down in the air, so you can use planes and drones and balloons to look at what's going on. So on the right there is a picture from a study by, and I think it's an Italian research group, where they've got these various cameras that they send up. I think they mainly use balloons to get data that proud. But of course, there are pros and cons to everything. It's pretty expensive to put a plane in the air. And when it comes to things like drones, you have to be careful about flight paths and so on. And again, you're not capturing a ground-based viewpoint with those as well. You can get ground-based panchromatic sensors. By that, I mean, it's a device that you just get one number out of it. So it's just telling you that it's 50 here, it's 60 here. So it's not telling you every sort of pixel. You're just getting one little thing at a time. So we get sky quality meters. They're very commonly used by astronomers and not very expensive. So you might like to have a go at looking at that kind of thing at the top. And we also get, you can get smartphone apps that you can see how clear the sky is. You can get illuminance meters, which again, I brought one from my lab to show you, luminance meters and wearable devices as well. So some studies, they get people to wear a device and see how much light pollution they're getting as they walk around a city. And there's the sky quality meter. It's really easy to use. You hold it and you push a button, and that's about as tricky as it gets. Interestingly, remember that I said before that the satellites didn't pick up blue. This is the other end of the spectrum, which it picks up a bit too much blue, which doesn't matter when you guys are just, you guys, astronomers, are just looking at to see sort of the sky quality. But for scientific studies, it's a bit of a pain because you're trying to compare this data with that data, and they've all got sort of different responses. Nothing's sort of calibrated against each other. And also, because they're easy to use, there can be problems with them where people just point and shoot, and they don't realize that there are precise operating instructions that you have to follow. It comes with a little leaflet. But people are using these to enter their light pollution data online into maps of the world, so you can see how things are changing over time, which is quite a cool sort of way of looking at things. Lots of words there, but if you're interested in using a smartphone app to measure light pollution, just remember that every smartphone has a different sensor on it, and so that means that everyone's going to get slightly different results, so we have to be a little bit careful there. Also, yeah, it's just inexperienced users sort of possibly getting information wrong again. Illuminance meters. There's a picture here. I brought this with me. You can get a sense of scale. It's a small little device here. They're really inexpensive, easy to use, and widely available, but it's really time consuming to do measurements because you have to do one measurement at a time, and they have poor sensitivity at low light levels, so that doesn't really work when you're trying to measure light pollution, which is hopefully not as bright as daytime. We also have luminance meters, which are these things here. This is the one from NASA. You can see there I am looking through it to give you a sense of scale again. That is used for looking at the brightness of signs and that kind of thing, because this one here looks at how much light is arriving on the surface. But this one here, you couldn't just hold it next to a sign. You need to look at the sign and see how bright the sign is. And so that's what the luminance meter is for. Unfortunately, they've got very similar names. So when I'm teaching, I normally have to sort of go luminance so people can hear the difference. And of course, we've got wearable devices, which can have calibration issues. It's all calibration is a really massive problem with devices. And then we have imaging sensors that we can also use from the ground. So we can take a big picture of the sky and we can look at every pixel and see what's happening in the sky. We can get imaging smartphone apps, and we can also get hyperspectral cameras as well, which look at all the different spectral data that we have. The digital cameras, an example being the bottom right there, very popular. They produce comprehensive data, and they can be used to measure the sky, or you can use them to measure vertical planes as well, which is really great to see, like an animal's viewpoint, for example. They do need a lot of calibration, though. It's quite tricky in that regard. You can get off-the-shelf options, but they're really, really expensive, the pre-calibrated ones. Imaging smartphone apps, they're fun, but the sort of accuracy is a bit of a problem again there. And hyperspectral cameras, they give you lots of information, but again, really, really expensive. We have to be really careful when we're using anything to measure anything, but especially light pollution, because the data, as we see there, can be misinterpreted and misused. So we've already talked about the blue blind satellites. So people will use that data, make all sorts of conclusions, and not realize that intricate part, that intricate detail, which is actually really, really important. Illuminance meters, they're so easy to use that people sort of wave them around, but you have to precisely report, I was measuring on this angle at this point and so on, which is something that seems to be missed by a lot of papers that I read as well. And then sky quality meter, this is something that I had read in an article which said that it's potentially tempting to adopt tools developed for other disciplines, such as the low cost and easy to use radiance meter sky quality meter. Unfortunately, in some cases, these instruments are being used for purposes beyond which they were intended. And we're concerned that the radiance data are unreliable because of the inadvisable use of a sky quality meter. So whatever you choose to use, if you're interested in measuring light pollution, make sure you read the instructions. That's basically what I say. So when I wrote my paper that I mentioned, I sort of looked at each meter one at a time. I looked at the four main ones. So I said an illuminance meter, yeah, it's really easy to use. It's pretty cheap. It doesn't really pick up the spectrum very well though. Then I looked at a digital camera. Oh, awesome, lots of data, great spectral range, but it's not very cheap and it's pretty hard to use because you've got to analyze all the data afterwards. Then I looked at the satellite. It's free, so that's definitely low cost. Get a pretty good amount of data. It's pretty easy to use once you know where to look, what to look at, how to do it. But spectral range, I judged it really poorly, of course, because the blue blind. So that's a big problem. This is the specific satellite that I was looking at. And then the sky quality meter that I mentioned, pretty low cost, pretty easy to use. Spectral range is not great because it measures too much brunner, and the amount of data is not great either because you're just getting a single point each time. So I kind of said, well, I'd like something that did everything. And so that's what my PhD is all about. So I developed a tool last year which used equipment that you possibly have seen before. So we've got a ZWA camera here, an astronomical camera. We've got a Raspberry Pi there with a little clock and so on. And I put it in this little weather-tight box. The idea being that I can set this up and leave it somewhere, and I can record data over a whole night, because a lot of these instruments rely on someone pushing a button to record data, whereas this all happens automatically. So this is what I'm busily working on still. By the way, I've taken all the cables out so that it looks nicer. So, so it does have cables to tie everything together, but I just wanted it to look neat and tidy. So you can see there's some little 3D printed mounts there, and nice little base boards and so on. Yeah, so that's where I'm at. And that's sort of where I thought I'd leave it. I've got a little bit extra, which goes into more technical detail about stuff, but I don't know if you're keen on that kind of thing. Maybe we'll just play with the instruments as well instead and see what's happening. And I would like to put up my great big list of references that we're preparing all the way through. So yeah, that's cool for me.